Hey folks, welcome to this episode on molecular polarity. So molecular polarity is all about whether or not the electrons are evenly distributed throughout the molecular structure. And the symmetry of the molecule is a large factor when you're determining this molecular polarity. When we're looking at symmetry, we're talking about asymmetry. These molecules tend to be polar. So asymmetry means that one side is not the same as the other. And what that means in terms of molecular polarity is we're going to be looking at bond polarity. So maybe one side has a polar bond while the other sides don't. And then the electrons will be pulled in one direction rather than the other. Symmetrical molecules are usually always nonpolar. So that means that they might have no polar bonds, in which they're symmetrically nonpolar. Or maybe one side has a polar bond going north, the other side has a polar bond going south, and they end up canceling each other out. It's not always that simple, but that's kind of the gist of it. And by figuring out the molecular polarity, we can now start investigating what kind of intermolecular forces are between these adjacent molecules. Once we know that, we can really start looking at the actual properties that these molecules have. Now, recall bond polarity and what makes a bond polar or nonpolar. It's all about the difference in electronegativities. If you have a large difference in electronegativity, well, if it's actually a huge one, you're just going to get an ionic bond. But if there is a difference in electronegativity, but it's not that massive, you'll get a polar bond, which means that one side will be pulling the electrons closer to its nucleus over there and be holding it more on that side. Because the electrons are more found on this side here, and remember the electrons are negative, it's going to have a charge of slightly negative. And this side, because the electrons are being drawn away from it, is going to have a charge of slightly positive. Now, bring that into ionic. What you'll notice is that there's a difference in charges here. When we're talking about ionic, they have a full charge. And that full charge comes from electrons being transferred. Okay, so electrons transfer. But in covalent bonds, remember that electrons are not being transferred, they're still being shared. Why do we get these partial charges? Well, they're being shared, but again, they are being shared unequally. This side has more claim to those electrons because of its higher electronegativity, and it will therefore be a little bit slightly negative. And we use this kind of vector arrow to show that kind of movement of electrons. We'll talk about that in a moment. Again, nonpolar means that both atoms, in this case, and this bond that's between them, is sharing these electrons evenly, and so that not one side or the other is more negative than the other. In this case, this side has more of the electron, more hold of the electron, and it's going to be more negative than this side. And just remember that we do have certain values that help us figure that out. So recall this, we did this in class. Again, to find what the difference in electronegativity is, well, we have to figure out what the electronegativities are. And for oxygen, that is going to be 3.5 minus 2.1 for hydrogen, okay? And we get 1.4. So if we apply that onto our bonding continuum, remember that bonding continuum that we had, we just briefly saw a basic version of it before in the last slide, we would see that this is going to be a polar covalent bond. So you can do the same for those, and this is going to be nonpolar covalent, this is going to be ionic, and this is an interesting one, but it's still going to be ionic. So polar bonds versus polar molecules. The key learning idea here is that a molecule that contains polar bonds might not be polar itself. Okay, like we said before, it's due to a combination of whether or not it has polar bonds, what's the magnitude of those polar bonds, and also the symmetry of the molecule. And that kind of, the magnitude of the polar bonds kind of fits into the symmetry of the molecule. So we have to look at the symmetry, whether it's symmetrical or asymmetrical, okay, the shape of the molecule, and kind of decide whether or not it's going to be polar. So to determine this, we first have to draw the Lewis structure of the molecule, and we've seen that before. Once we do that, we go to our electronegativity chart and label the electronegativity values of all the atoms in that molecule. Now what you'll start seeing is that you'll be able to find out the electronegativity differences of each bond, and you'll be drawing these little vector arrows to show the direction of the movement of electrons. Now once you draw this, if we're pointing electrons, so this vector arrow will be pointing towards the most electronegative atom of the two. Now what does that mean? Well, this most electronegative atom will be pulling the electrons closer to itself, and therefore it's going to be slightly negative This side is going to be having the electrons pulled away from it, and it's going to be slightly positive. So we use these partial charges, as they're called, to show where the electron density, or the density of electrons, where the electrons are going to be held, are found. They're usually going to be found around the electron or the atom that has a higher electronegativity, and because that's so, they're going to be slightly negative. Okay? Now, once we figure out all the bond polarities, or if they're nonpolar, that could also be the case, we then look at the symmetry of the molecule. Now, it's not as simple as a 2D molecule on the paper, because remember, these molecules are 3D. So we are going to be working with that a little bit and trying to figure that out. But in general, if a molecule is symmetrical, and they do have dipoles, they will actually cancel out and the molecule will be nonpolar. However, if it's asymmetrical, so maybe, for example, if we have 4 bonds, let's use carbon for this case, we have hydrogen, 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 and we have fluorine. Now, all of these bonds, these carbon-hydrogen bonds, they're not going to be polar. They're going to be all nonpolar. Okay, so there's equal pole. But between the bond between carbon and fluorine, fluorine is a lot more electronegative. It's going to be slightly negative and slightly positive. So in that case, that bond is going to be polar. Now, to figure out what the molecular polarity is, we have to look at the whole thing here. We see that this is not a polar bond, that's not a polar bond, that's not a polar bond, but this is a polar bond. So this part of the molecule on the top here will be slightly more negative than this central atom, or the bottom of the molecule here, which is going to be slightly positive. Because this side is more negative than this side, we've created a overall molecular dipole. Okay, molecular dipole. And if we have an overall molecular dipole, it means that the molecule is polar. Okay? So we have to look for that molecular dipole, and then if we have that, we know that the molecule is going to be polar. The molecular dipole is basically a sum of the bond dipoles. Now, again, we use this vector arrow, which in chemistry is called a dipole moment. And it's a quantitative measure of the polarity of a bond. So in this case, when we're drawing it, we're just drawing an arrow. But there is a way that we can actually quantify how much pole there is, and that kind of difference. And it's a quantity, it's a vector quantity, because it both has magnitude and direction. So if, for example, hydrogen was bonded to fluorine, there would be a larger magnitude pull towards fluorine. But if hydrogen was bonded to chlorine, that magnitude, let me just visually draw this. Okay, there's a certain amount of magnitude in that pull. But again, if hydrogen is bonded to chlorine, there is still a pull towards chlorine, but the magnitude is a lot less, because the individual electronegativities of fluorine compared to chlorine are different. It's En. There we go. Okay. Fluorine's electronegativity is a lot larger than the ones of chlorine, so that pull will be different as well. And here are just some diagrams over here to show what that means. In terms of carbon dioxide, one thing just to add to this carbon dioxide is that it's actually a double bond. Okay, so you have one bond here, one bond there. Same thing here, there. Now what we see is that when we look at the electronegativities, the electronegativity of oxygen is 3.5. This is 3.5, it's the same atom. And carbon is going to be 2.5. So what we see is that there's a difference in electronegativity of 1.0 for both of these. Now, if we remember back in our bonding continuum, that means it's a polar bond. Now, which one is the more electronegative atom? If you said oxygen, you're absolutely right. Oxygen is the more electronegative atom. And that means that it's going to pull the electrons closer to itself, hence this vector arrow. Okay? It's showing that the electrons are being pulled closer to oxygen. Now, if the electrons are being pulled closer to oxygen, what does that mean in terms of its negativity? Well, remember, the electrons are negative, so it's going to be slightly negative. Now, the same thing is happening on this side. Again, the electrons are being pulled towards this oxygen, between that carbon-oxygen bond, and it's becoming slightly negative. But what we see here is that if we're pulling this way with the same magnitude, because it's the same atom, and we're pulling this way with, again, the same magnitude, because it's the same atom, what happens? Well, if we're thinking about a tug of war, and there's a little flag in the middle here, and we're trying to move that flag, where's it going to move if we're both pulling the same? It's not. And so that's why there's no net dipole, and this ends up being a non-polar compound. This side is just, this one right here, is just as negative as this side, so there's no difference in terms of positivity or negativity from one side or the other. We're going to talk about water in a second, but we're going to work that through a little bit. Now, the one thing to remember is this little acronym called SNAP. It stands for symmetrical, nonpolar, asymmetrical, polar. So if the molecule is symmetrical, which means the dipoles cancel out if there are any, then the molecule is going to be nonpolar. If it's asymmetrical, one of the dipoles doesn't cancel out and there's a net molecular dipole, then the molecule is going to be polar. Okay, so what you have to start realizing is that we are pairing the polarity of bonds to the polarity of molecules, and we're relating them. And if the molecule is symmetrical and those bond dipoles or the bond polarities don't cancel out, we will be polar. But if they are symmetrical and they do cancel out, then we are going to be nonpolar. Now, a couple other things that we have to take into account about polarity. A molecule is nonpolar, again, if each bond in the molecule is nonpolar and there are no no lone pairs on the central atom. Okay. Or each bond in the molecule has the same polarity and there's no lone pairs of electrons on the central atom. Okay? So what that means is overall there's no net dipole moment. There's no molecular dipole. All the bond dipoles cancel out. However, a molecule is polar if there is a net dipole. So that means that something hasn't canceled out. Now this could be the reason because each bond in the molecule is nonpolar, but there are lone pairs of electrons on the central atom. So that can actually cause an area of negativity. Or the bonds in the molecule, they have different polarities, or there are unbonded electron pairs in the central atom, and again, that's causing an area to be more negative than the other. So I'd really like you to copy that down in your books. So if you want, you just rewind a little bit and record that into your notes, and let's actually work some of these things through. So here we have water, and water here is a Lewis dot diagram. Remember that hydrogen is stable with 2 electrons. Oxygen needs the 8, so it has 2 lone pairs over here. Now, so this is our central atom. The reason that this is our central atom is because it is at the center of our other 2 bonded atoms. Now, what we notice is that there are 2 lone pairs here, which is going to automatically create this kind of area of negativity. Remember, these electrons are still negative. They're still going to be a little bit negative there. Now, in this case, what we have to look at is first, let's establish the electronegativities. Looking on the periodic table, we know that hydrogen is 2.1, this is 2.1, and the electronegativity of oxygen is 3.5. So, we have to look at these differences in electronegativity. Which one is more electronegative, oxygen or hydrogen? Now, hopefully you said oxygen, and what that means is that we're going to draw these dipole moments towards oxygen, showing that the electrons are being pulled towards oxygen. The same thing goes for this bond over here. So what we've created is we actually say that we have 2 polar bonds. Our first polar bond is right over here, okay, electrons being pulled towards oxygen, and this one over here, again, electrons being pulled towards oxygen. So if the electrons are being pulled towards oxygen, what does that make it? Well, it makes it slightly negative. And if the electrons are being pulled away from the hydrogen, what does that make them? Well, again, they're going to be slightly positive. So what we've established, we've established 2 bond dipoles. There's this dipole over here, positive and negative, and there's this dipole over here, again, positive and negative. Now, what we have to figure out is if the molecule is symmetrical or not. So what we can do is we can kind of split it down the middle this way, and we can see if this side is the same as this side, and it is. Okay, it's the exact same on both sides. Now, however, if we split the molecule this way, we can see that this bottom side is not the same as this top side. Again, if we split it down the oxygen, that being our central atom, we notice that this side is a lot more positive than this side is over here. So what does that mean in terms of molecular polarity? Well, there's going to be an overall net dipole in this direction here. This side of the water molecule will be more positive because both of these hydrogens are positive. So this whole area of the molecule, if we kind of make it into a 3D look, this whole area here or that whole area here, all the area at the bottom there, is going to be more positive because both of these hydrogens are positive. So that makes this side of the molecule slightly positive. Now, if we look at the oxygen parts, not only does it have two lone pairs that are very, very negative, but also the electrons are being drawn towards the oxygen. So putting those things together, and because there's no way that these will be able to cancel out, this side of the molecule is going to be slightly negative. So if we draw it onto these 3D molecules here just to see it, this is our whole kind of molecule. We'll just kind of draw a little boundary around it. This area at the top, this whole area will be slightly negative, and this whole area at the bottom will be slightly positive. And what we see is that we've created a dipole, okay, going in that direction there. This is negative, this top side is negative, this bottom side is positive. So is this a polar molecule? Yes, it is. Water is polar. Okay? It's not symmetrical, it has polar bonds, and it has lone pairs on the central atom. It is a polar molecule. Now let's look at methane now. We have carbon bonded to 4 hydrogens. So once again, what we need to start off with is by identifying the electronegativities of each atom. 2.1, 2.1, 2.1, 2.1. Carbon, again, would be 2.5. So if we look at the electronegativity difference, now we can just calculate one of these, and it'll be applicable for all of them. So let's just take this one over here. Let's calculate that electronegativity difference. 2.5 minus 2.1, and we get 0.4. So based on our bonding continuum, this is a non-polar covalent bond, which means that all of these bonds are non-polar covalent, non-polar covalent, and non-polar covalent. Now what does that mean? What does that non-polar covalent means? Well, that means that there's no one atom that is pulling more than the other. There's a slight difference, 0.4, but it's not enough to actually make that into a polar bond. So that means, what does that mean? It means that all the electrons are equally distributed in the molecule. So if all the electrons are equally distributed within the molecule, is one side of the molecule more negative than the other? No. Okay? We don't have any lone pairs on the central atom, which means that there's no area of negativity. And there's no lone pairs on any of these atoms over here, so there's not one side that has more negativity. There's no pulling in one direction or the other, so there's no slightly negatives, no slightly positives. So all of our bonds are nonpolar. If all of our bonds are nonpolar, our whole molecule is also going to be nonpolar. Okay? There is symmetry in this molecule, and we can see that all of these are the same. But in this case, it doesn't even matter because all of the bonds are nonpolar. You can't look at and get a polar molecule if we don't have any unequal pull of the electrons. So here we can look at the 3D kind of models of carbon with the 4 hydrogens, the methane. And you can see that it's a little bit interesting. They have this very interesting tetrahedral shape that kind of moves around. So if, for example, one of these atoms were substituted with a fluorine, for example, then there would be a molecular dipole because all the electrons, or not all, but a lot of the electrons would be being pulled towards this side, and that would create a polar molecule. But with all the atoms being the same, with all the bonds being nonpolar, and with this molecule being symmetrical and no lone pairs, we know that this is going to be a nonpolar molecule. So here are some other ones. You can see that the first 3 are polar molecules. The reason for that is, again, when we have chlorine is a lot more electronegative than this hydrogen here. So it's going to pull the electrons, making this side slightly negative and this side slightly positive. Now, is there anything to cancel this dipole out? No, because there's no other bond in the opposite direction. So that means all the electrons are moving to this one side. This is a simple molecule with only one bond. So that bond is polar, and it makes the whole molecule polar as well. The whole molecular dipole for this one would be in the same direction. It would be in this direction right here. And the molecule would be slightly negative on this side and slightly positive on this side. Now, if we look at the second molecule, one thing that this is missing, and again, same with the chlorine, there are actually lone pairs of electrons here. this nitrogen has a lone pair of electrons over here. So not only is it already negative on this side over here, but also you can see all the bonds are polar, being pulled towards the nitrogen. That makes all the hydrogen slightly positive, slightly positive, slightly positive, and this makes this nitrogen very slightly negative. So if we compare this bottom side here with the top side of the molecule, what we can see is that this whole bottom side of the molecule is much more positive than this top side. And so therefore, we do get an overall molecular dipole, and our overall molecular dipole will be in this direction. This will be slightly negative, and this side will be slightly positive. If we look at the third one over here, once again, we need to put our lone pairs on our chlorine. Okay. So we only have one polar bond here. So what we have to see, and this is our polar bond that makes this carbon slightly positive and this chlorine slightly negative. What we have to figure out here is, can this polar bond be canceled out with any other bonds on this side? But what you see right away is that all of these bonds are nonpolar. So if they're nonpolar, they can't be pulling up in the opposite direction. They won't be able to cancel out. So the overall molecular dipole will be in the direction of chlorine. That's where the electron density is going to be at. This side will be slightly negative, and this side will be slightly positive. Looking at the two examples over here, boron trifluoride, what you see is that there are polarities in all directions. You see it over this way. This makes it slightly negative. Again, here, fluorine becomes slightly negative. And again, here, slightly negative. Again, the arrows, the vectors show that the electrons are moving towards the fluorine, and so it's going to be slightly negative. So that means boron is going to be really a little bit more electrode deficient, and so it's going to be slightly positive. But what you can see, and this is actually, and it's a shame that we can't move these molecules, but this is actually in the same plane. So if you kind of moved it up a little bit, you'd actually see that it's all in the same plane. There's no projections. It's a flat molecule. And because of that, what we see, and this is the best way to kind of visualize it, if we have a circle and we divide it by 3, okay, we're going to get this kind of figure. Okay? And what that means is that all of these poles are all going to be in opposite directions. If they have the same molecule, which they do, fluorine, 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 it means that the magnitude of the pole is the same. And if the magnitude is pulled the same and they're all pulling in opposite directions, that means they're going to cancel out, resulting in no net dipole. So this molecule is a perfect example of how a molecule can have polar bonds, but there's no resulting molecular polarity. The same thing with this last one over here. All of these should have lone pairs, so we're just going to quickly draw that. Oops, that should be paired together. Okay. So in this molecule here, again, we have 4 polar bonds. This way, again, going to chlorine. This is slightly negative, slightly negative, slightly negative, and slightly negative, making carbon slightly positive. Now in this case, because, again, they're pulling in opposite directions, and the magnitude of their poles are the same. The reason the magnitude of their poles are the same is because they're the same atoms, the same bond. Okay? It makes them all slightly negative on the side, but it also cancels them out. They're all pulling in opposite directions with the same amount of pull. So say, for example, we had again, tug of war. Here is the flag in the middle, and we had 4 individuals on this side, and they're all pulling outwards. They're all pulling this way, this way, this way. What you're going to see is that this center won't actually move. Okay, if everyone's pulling in opposite directions with the same amount of magnitude, that center is not going to change, and so it's kind of the same reason in the molecule. All the dipoles, all the bond dipoles or the dipole moments cancel out, and there's no resulting net molecular dipole, so that means that the molecule is nonpolar. Alright guys, that's it for this episode. Thanks for watching. See you next time.